Well, today we're going to talk about how system calls are built at a high level and also some of the challenges or dangers that operating system kernels have to be aware of in providing system calls to user programs. These things will be immediately relevant to your second Pintos project. It's project 3 in CS124, but yeah, this knowledge is going to be super helpful. There's a lot of details you'll have to work through, but at the very least, this will get you started on how you need to tackle the project. So let's go ahead and get things started. User applications have to interact with the kernel, but remember there's this barrier between the two, this separation of user mode from kernel mode, and you can't just switch into kernel mode willy-nilly without any control. And so the primary mechanism that user programs have to get into kernel mode is actually provided by the operating system itself, and it usually involves some kind of trap mechanism. So you have some instruction on x86, it is int, but that's not the only way that it's done. I was just thinking about ARM processors this morning, since I know the Raspberry Pi is an appealing operating system platform for operating system courses. And it has a specific instruction for trapping into the kernel, and it's not an interrupt instruction. It's a very specific kind of trap instruction. And same thing with x86-64. Now we have sysenter, sysleave, and syscall, sysret that are used for getting into the kernel. So different mechanisms, but the OS sets it up so that all of these transitions from user mode into kernel mode are very carefully controlled. Now the kernel registers a specific handler. We're going to be very specific with IA32 at the moment. You can see I have the various interrupt numbers listed on the slide. Hex 80 or 128 is very common for 32-bit Linux, and then Pintos will use 30 hex. That'll be the interrupt number that Pintos uses. That code is already provided for you, but you will see in the interrupt handler for that interrupt number that it goes to the syscall implementation for Pintos. It's really kind of difficult to pass arguments on the stack because the system call handler actually operates with a different stack than the user space program that invoked it, or the user mode program that invoked it. Remember that on most of our modern processors, different operating modes have different stacks because we want to isolate the operating modes from each other, especially if we have different protection levels and very different capabilities in these different modes. So it's almost always that the arguments are passed in registers, and then the return value or whatever, if it's well, there's various approaches that are used for this, but typically the status value itself is returned in a specific register, which is then available for the user program to examine. So that tends to be how these system call implementations work. Pintos is a little different. Pintos uses the stack, and I think the big reason why Pintos uses the stack is to force you to think about how to access user space data from kernel mode. And so we'll talk a little bit about that toward the end, but normally you would just pull stuff out of the registers because the arguments to the system call would be squirreled away in registers. Okay, so as it says here, one of the arguments to the system call is a number saying which system call you want to invoke. So on Linux and on Windows, that would be an EAX. So let's stick to 32-bit. It would be an EAX. And that just says this is the operation I want to perform. And so you can have any number of arguments up to typically 6. Some Windows API calls have more than 6 arguments, but you'll have some maximum number of arguments that tends to be accepted by system calls. And so there's code that invokes the system calls for you, puts that system call number in, and packages up the arguments as necessary. Now, there is an obvious constraint from this, which is that the arguments that you pass to your system call functionality have to fit within a register. So if it's a byte, no problem. If it's let's say a short, a C short, so it's 2 bytes, then that would be fine too. On IA32, it would be a maximum of 4 bytes. If you have anything larger than that that you intend to pass, then you have to start being clever somehow. And it's not like it's a difficult problem to solve, but it tends to be that the OS has to specify, here's the convention of how this works on this operating system. So larger arguments can be split across multiple registers. If my memory serves me well, then that is the general Unix approach, is that it'll just split a larger argument. Like, let's say that you are seeking in a large file that has a file offset larger than 32 bits, then it may pass it in a couple of registers. Or if, as is normally the case on Windows, if you need to pass a chunk of information, you can just create a struct and then pass a pointer to the struct. And the kernel can certainly access the contents of the struct that you pass to the system call. So there's various approaches. You will notice that certain operating systems follow a certain pattern. Now, the system calls themselves, you have this mechanism where you have to have some trap instruction, and you have to package up stuff into some registers or stack or who knows what. What a pain in the butt to have to deal with all that yourself. And so the standard library tends to expose all the system calls through standard C functions that are easy to invoke from C code, obviously easy to invoke from C++ or Rust, and invariably, if you're talking about something like Python or any other language, they will be wrapped into something that's specific to that language. So the operating system has a standard library that sits in user space that is taking care of making it simple for user programs to use these functions. So that library does serve as an intermediary between applications and the operating system. And it's kind of interesting because not every function is just a direct passing from user mode to kernel mode, just pass through of the arguments. The read function is an example of a function that is just a very simple shim from the user application into the kernel. The read function, the system call itself, takes exactly these arguments, file descriptor, what buffer you want to read into, and the number of bytes to try to read, and those are packaged up and sent straight to the kernel, okay? But there's other functions that provide a lot of functionality in user space and in user mode, but they invoke the kernel when they need to. So malloc is a great example because there's this thing called the memory break. There's other names for it now, so that tends to be a more traditional name for this point, but it's basically the point in the address space where the heap ends. And so above that, the OS knows is not available yet, and below that will be the memory heap. And malloc will try to allocate space within that heap. And if malloc discovers that it's almost full and it needs to increase the size of the heap, then malloc will call sbreak or various other, more recent versions of sbreak to increase the size of the heap so that malloc can then have more available memory pool to satisfy allocation requests. So it really depends on these standard libraries, what their intent is, how much can be done in user mode versus requiring kernel intervention. But many of the system calls, especially the ones you'll be implementing, are direct pass-through because the kernel has to take care of stuff for you. Now, we did talk previously about how interrupts and traps work on IA32. Remember, IA32 is a specific instruction set architecture for x86. It's not the current one. Most people nowadays use x86-64, but IA32 is the one that Pintos uses, and it used to be popular, really popular, 15, 20 years ago. So user process has a stack, and the kernel thread also has its stack. Remember, the kernel thread stack is very small. And so when you trap into the kernel, the CPU does a certain number of things. So we save the stack pointer to the user stack since we're switching protection levels. Then we save the pointer to the instruction we were on when we trapped into the kernel. So that's the caller's code segment. That's what CS stands for, and the caller's instruction pointer. And it just has an E on the end because it's IA32. And the original 8086 instruction pointer was just IP. So now we have EIP, and x86-64 has RIP. So we store all of that stuff. And then the OS has these interrupt handling stubs that take care of configuring the kernel thread stack so that everything is uniform, so that multiple interrupts can be handled with a single handler. So for interrupts that don't have an error code, the OS kernel will push a dummy error code, which is, I think in Pintos, it's just 0. The stub pushes the number of the interrupt onto the stack so that the handler doesn't have to know. Like you could have a handler that handles multiple interrupts, and it can just look at the interrupt number and decide what to do based on the interrupt number. And then the register state of the interrupted program is saved onto the kernel stack as well. And this becomes really important because if you think about it, the user program was doing something, and this register state captures the values that were important to the program when it was interrupted. So we're going to talk a lot about this today. Also, we have the instruction pointer in the code segment to go back to when we go back to the user program, and also the stack so that we can access the user stack if we need to. If anything is passed on the stack, we can access it this way. Now the interrupt service routine can run, and of course that is exactly what it does. Now the information that is on the kernel thread stack is exposed into the interrupt service routine. There's a thing, many of you probably noticed this as you were working on the first Pintos project. There's a thing called interframe. Interframe is a struct in C with members that will appear at all the right addresses to allow you to access these things, so that the kernel can now access and manipulate user program state from inside the kernel in C code, which makes it super easy, relatively speaking. It's certainly a lot easier than assembly code, but it's quite easy then to manipulate user program state as needed by the kernel. So the system call handler also has to return a status result. And this is what I want you to think about, because the kernel handler is doing stuff. The kernel handler needs to see the user program's EAX to see which system call was invoked. Well, all it has to do is come into the information passed in the interrupt frame, and the register state of the interrupted program will have a field named EAX, and it can just look at that field to see what the user program passed. And when it needs to return a value to the user mode program, saying this is what happened with the system call, it can go and mutate the register state of the interrupted program. So it can set EAX, the field in the interrupt frame, to whatever value it needs to set it to. And then when that thread switcher runs and we restore all of this machine context and switch back to the user program, the program will observe its EAX set to whatever the kernel said it should be. So this is a really clever mechanism, and I just think it's really powerful and really neat that we have this way of telling the user program what happened via the register state using this mechanism. Okay, so I already talked about that. The system call operation that's being performed has an ID associated with it. And so you might say to yourself, well, how do I take that numeric ID and then figure out what operation to invoke? And not just that, but these different operations take different numbers of arguments. So how do I construct the program to do that mapping or do that routing properly inside the kernel? And it turns out to be pretty straightforward to set up. The actual implementations of the calls are called system call service routines. You'll sometimes see it abbreviated SCSR, but I try to avoid ever doing that because it's kind of a confusing thing to have an acronym for. But the service routine for the system call is the function in the kernel that implements the operation. So if you have an operation like write or an operation like fork, the kernel might have a function called syswrite, sysfork. And that indicates, the naming of it indicates that this is a service routine for a system call. The other thing that's really nice about this is if you have sys this and sys that, then you can invoke them from other operations when you need to perform more complex tasks that interact with the user mode program. So there's some really useful things that you can do with this kind of approach. Generally, I would say that I probably see about 50% of students follow this naming convention in their kernel implementations in Pintos. I hope all of you will. It's a really nice one. But we don't actually get terribly cross if you do something else, unless it's just really confusing and will lead to bugs. That tends to be what we tend to penalize for in this class, is just code style and structure that will make it harder for you to write good programs. So we try to discourage that. Okay, now how do you dispatch to this? Well, the way that some operating systems do it is they use that system call number as an index into an array of function pointers to these system call service routines. Now, I don't know if you're very comfortable with that idea or familiar with the idea of initializing an array. It would be some kind of static member in a module. So a static global variable is how I normally describe it. Really, probably the most accurate term to describe it in C would be a module level global variable, because it's still only visible within the module. But you have an array of these function pointers, and then you use that array, you index into it to dispatch to different service routines. Now, there's an easier way that may be more intuitive for you, which is just use a freaking switch statement. Switch system call number, case this, case, and then you invoke a function, break, case that, invoke a function, break, and so forth. And the compiler will turn that into, surprise, an array of function pointers, and it will use the system call number to dispatch through that array of function pointers. So you can do it either way. At this point in my life, I'd probably use a switch block, because I value clarity over cleverness, because a lot of times being too clever will actually work against you. So just make stuff clear and maintainable, and it'll be easier to debug and easier to understand. Okay, let's see. Yeah, so you do need to make sure the system call ID is valid. If you're sitting there thinking about, okay, so there's a table. Donnie, let me get this right. There's a table, and you index into it with a value provided by a user program. That seems fraught with peril, and that would be right. So the system call mechanism verifies that the ID is valid, and there is actually a specific return value. I don't know how many of you read carefully through man pages as you were implementing your command shell for the first project, but there's actually a syscall function, and if you try to invoke an invalid system call, it'll return an error saying no sys. There's no function for that system call number. And so the easy thing to do is just check if it's below the max. Make sure it's an unsigned value. So, if it's below the max, then the lowest it can be is 0. And then that's one part of it, because if it's above a certain value, it will be invalid. And if you have other system call numbers that are invalid, then you can actually map them to a function, a system call handler, a system call service routine, whose whole job in life is to say, I don't exist. So all that system call service routine does is say, sys. That's all it does. And then that makes it really simple to build a system call dispatch mechanism that validates system call numbers and tells the user program when it's not valid. Okay, so here's a little bit of assembly code. You do not have to implement yours in assembly code, but I just thought you'd like to see this, because this is how it works in an advanced operating system like Linux. So you have all the stuff for when you enter into the command shell. I've got command shell on the brain. When you enter into the kernel, you save all of the user program state onto the kernel stack. And then this pair of instructions compare EAX, which contains the system call number, to how many system calls you have. If it's above that, then you know you have a problem. If it's below that, then you skip over the "you have a problem" code. So this just moves enosys into the place where EAX will be restored from, and then it returns from the system call. So this handles returning enosys if the system call number is too high. Otherwise, we get to this code, which dispatches through the system call table using the EAX value, because remember, that's the system call number. Using that, it takes it and multiplies it by 4 because IA32 pointers are 4 bytes. So EAX is multiplied by 4, and then we index into the system call table, and we invoke that function. This is like the same kind of code you would get if you used a switch block. So I'm like, use a freaking switch block. Don't mess around. Like, why make life trouble? And then, as it says here, once system, this function is invoked and returns, its return value will be an EAX. And so the code moves EAX into the place where the user program's EAX will be restored from, and then it returns. So simple mechanism. And fortunately, like 95% of this is taken care of for you. I think you may need to say if there's an invalid system call number, but it'll just be a C function that returns a certain value. It's not going to be anything particularly difficult that you have to navigate. Okay, let's see. Different system calls require different numbers of arguments, and so this is another challenge that you have to sort out, and this is going to be relevant to you with the Pinto system call mechanism. You have, as examples, get, PID, and fork, which take 0 arguments. You'll pass a system call number, but that's it. And then this fancy pants mmap function, which changes the virtual memory mapping of a process, this thing can take up to 6 arguments. So you can imagine that's a lot of information to pass. So the system call arguments are going to be passed from the user process in specific registers. Now I should probably be specific here. On IA32 Linux and on x86-64 Linux and on Windows, system call arguments are passed in specific registers. If you're talking Pintos, Pintos does it differently because Pintos is an instructional operating system and wants to give you experience accessing user memory. So this is the real world discussion right now. EBX will be the first argument, ECX is the second argument, and so forth. Okay. Now these service routines are written in C, as I was saying before, unless you're a more advanced operating system implementation and maybe you have some C++ as well, whatever. And generally on IA32, there's a specific calling convention by which functions receive their arguments. And so we'll talk a little bit about this. The way that the kernel thread stack is initialized to invoke the service routine. Remember this ... up here? This is all the interrupt frame and all of that other stuff, the user program state that was saved. But then the service routine dispatcher will save the arguments in reverse order. And remember that on IA32, on x86, as you push stuff, the stack pointer moves downward. And so you push arg6 first, that's the highest address, arg5 is at the second highest address, arg4 is at the third address, and all the way down to arg1, which is at the lowest address, but it's also the top of the stack because IA32 is confusing. Okay? Now, it turns out that this works really well with the cdecl calling convention. That's exactly what cdecl specifies. So they're pushed in reverse order. And so part of the reason why function arguments are pushed in reverse order on cdecl is because it's possible to have situations where you provide more arguments than a function actually requires. So if you push 6 arguments and the function only needs 3 arguments, the stack will look completely the same as far as the 3-argument function is concerned. It will simply ignore the subsequent arguments that have also been pushed onto the stack. Okay, and this is really helpful for building a service call or system call service dispatcher. So system call can basically, so remember how I said that some system calls take 0 arguments and some take 2 and some take 6? Well, the system call handler can always push 6 arguments onto the stack and then just dispatch to different service routines. And if a service routine only needs 2 arguments, it only accesses 2 arguments. But everything has already been initialized the same way, so the dispatcher can just dispatch to any system call implementation that's part of the kernel. So this is a simple example. syswrite. Remember, write is a system call function that takes 3 arguments: file descriptor, a buffer to write, and the amount of data to write. And it returns a value that is how many bytes were successfully written. Or if it's negative, it will be indicating an error. Probably not enosis, because it's definitely a system call. So that will be translated into a call to a system call service routine called syswrite, and we need to pass it file descriptor, buff, and size. And so you can see that the way the stack will be initialized, file descriptor is the first argument after the system call number, so it gets pushed last. The second argument gets pushed second to last, and the third argument gets pushed third to last. And then the other arguments that are unused also get pushed, but they're not used. And so when the syswrite function is invoked following the cdecl calling convention, the stack is just magically perfect. It's just the way that the service routine needs it to be. And so syswrite can access its arguments using the completely normal C type mechanism. It can return a value, it'll go back in EAX, and the system call dispatcher can take care of packaging everything up and making sure it gets back to the user program. So it's kind of a beautiful mechanism. Now, do you have to do it this way? You really don't. I think that the solution implementation uses a mechanism like this so that everything is very generalized, but you certainly don't have to. It may be that in your switch block where you're dispatching to various functions, you just call the function with the number of arguments it needs. That's fine. We're not going to penalize you if you don't try to create this generic mechanism. But if you also want to give yourself a challenge and see maybe a little bit more of how modern operating systems tend to implement these things, you can try implementing something like this and see if you can get it to work. So there's lots of opportunities to explore different implementation approaches in this project. Okay, next thing to talk about. We have this system call service routine that's handling some operation on behalf of a user program, and it just received arguments from that user program. Should it carefully consider the arguments that were handed to it before carrying out whatever operation should be performed? And this is, again, one of those things that you probably aren't used to in your programs. When you write one part of your program and you call a function in another part of your program, you probably do little to no checking to verify that the arguments are safe. Now, maybe you understand this thing called design by contract, or maybe you understand the value of using assertions, and so you put assertions to check your arguments, and you put assertions to check your return values. That might be something you do, but in this kind of context, the stakes are way higher, because one program may be some program you just downloaded off the internet, and another program is your SSH client with your SSH private key, and another program is a web browser you're using to access your bank account. So you have lots of very important information, and the OS needs to make sure to keep everything safe and separate. So this is like the biggest question you need to think about for this project, and probably for the bulk of your Pintos projects. Are there potential security holes in accepting pointers as arguments to system calls? What kind of trouble can you get into if you don't verify that pointers are actually valid when you get into system call implementations? Here's a simple example. Read is a system call. I say, here's a file descriptor. Here's where I want to read data into. Here's a pointer to a buffer. And this is how many bytes I want you to read into this buffer. Okay. Seems reasonable, right? I want to implement something like scanf or fscanf because I want to be able to read from a file and the OS has to do that. So the implementation uses read to ask the kernel to read data into a buffer. So yeah, you have these things, a file descriptor, pointer to the buffer, and a number of bytes to read. So we hope and expect, like on a good day, that the buffer pointer would be in user space. Now, what if it's not in user space? What if a user program tries to access kernel space? Well, if the user program tries to access kernel space, the CPU says no, and it generates a protection fault. And so the kernel finds out that the user program tried to access kernel space, and almost 99, unless you configure it manually yourself to do something else, that process is getting terminated. But what if the user program passes an address in kernel space to the kernel? Can the kernel access it? And the answer is definitely. The kernel can do just about anything. And so this is one of the major issues that you have to think about when you build system call implementations. If a user mode program passes along an address that's important in kernel space and the user program didn't touch it, it just passed it, and says, hey, kernel, here's a pointer. Why don't you go ahead and use it? The kernel has to be very careful not to make mistakes in what it accesses. So like it says here on the slide, as long as the user program doesn't access the address directly, it can just say, it can construct an address and just pass it, but it doesn't dereference it, no problemo, no fault. You're fine. The thing is, the kernel is allowed to write to the address. And so the kind of thing that you could get into is if the user program was trying to target kernel data structures, like maybe something that controls process scheduling, maybe something that controls process privilege levels. And so you construct a file of data and you say to the kernel, hey, read this file and read it into this address that's in your own address space. And a good kernel will say, absolutely not. I don't want to do that because that's not safe. So this is a major issue that all of you will have to deal with when you implement your system call handlers. Now, it turns out that you can get to 90% of the solution with one simple check. It sounds kind of like one weird trick that hackers hate or something like that. But the simple thing you can do is say all addresses passed to system call handlers have to be in user space. Now, the picture on the right of the slide is what the address space layout of a 32-bit Linux process looks like, or a 32-bit Pintos process, because Pintos uses Linux compilation to generate user programs, because why reinvent the wheel? And you'll notice that there's this magic address here, C0000000. That is also the 3 gigabyte boundary. So it's a 4 gigabyte address space. The bottom 3 gigabytes are allocated to the user program. That doesn't mean that there's 3 gigs of memory available. It's just 3 gigs of address space. And the top 1 gigabyte of address space is the kernel's. So as it says on the right, the top gig will be kernel mode only for access, and the bottom 3 gigs will be user mode or kernel mode access. Okay, and like it says, if an address in kernel space is accessed from user mode, it generates a protection fault, is what it generates. So the easy and fast way to verify addresses is just to say, is it below this boundary, the user kernel space boundary? And in Pintos, it has a name, and you should use the name and not the number. The assignment write-up is really clear about this. But if the address is below FizzBase, then that's your first step of checking. If it's FizzBase or higher, is not trustworthy, and the service routine should go ahead and carry out the appropriate error behavior in that situation. Okay, so that's the first thing. So as it says here, addresses below the kernel user boundary could still be invalid. I don't know if any of you have dereferenced null lately. I don't know if any of you have tried to use a garbage pointer and or an uninitialized pointer is what I mean by that phrase, and had your program crash. I certainly have. The only reason I haven't recently is because I do a lot of programming in Python these days, and that's a little harder, but still not impossible to achieve. So you pass a pointer to unallocated memory to something like read, or you pass a pointer to read-only memory to write, which write is supposed to be writing into the buffer. So if you pass a pointer to read-only memory, you should see a fault. Again, you should see a protection fault. So you see a fault in those situations, and the OS has to understand what that means. And so this is sort of the big challenge. The only issue with this is that it's not always an error to see a fault in the kernel. Because most of the time OSs follow something that either is explicitly demand paging or approximates demand paging. There may be some prefetching the OS does for performance, but demand paging means I'm not going to give you a page frame for this address range until you start using the address range. The minute you access the address range, the kernel says, okay, here's a frame to put your data in, and then you can go ahead and read and write that address range. So the fault mechanism also may simply be normal. You also have other things like copy on write, which I don't know if you've seen this phrase before, but copy on write is a clever mechanism for allowing two processes to think they have isolated address spaces. Like when you fork, you have a parent and then it goes whoop, and then you have a child. Well, maybe I need to turn my hand so they're more identical. But the child is supposed to be a mirror copy of the parent. But if the child starts mutating its state, it shouldn't affect the parent's state. And so copy on write is a mechanism to implement that, where the pages of the parent are marked copy on write. They're also marked read only. And if the child writes to a page, then the kernel swoops in and duplicates the page contents and gives the child its own copy. So you'll only duplicate the actual pages that the child changes. It's a really clever mechanism. So you see that faults can occur in buggy scenarios where the user program is being naughty. You have situations where a fault is normal. It's the normal operation of the virtual memory system. It may be something that the kernel is doing to present a clever abstraction like copy on write. And there's another scenario where you can have a fault, and that's if the kernel has a bug. So you have to somehow discern between these as you implement a kernel. Now, the one nice thing for us is that you don't have a virtual memory manager yet. In fact, that'll be the next Pintos project, and it's kind of scary because the project write-up basically says, go to this directory and implement virtual memory. And you go into the directory and it's like empty. So it's like, oh man, I gotta start from scratch. So that's kind of an exciting project to do. For most students, they're like, what am I supposed to do? We have a whole discussion of that. So we'll talk about that when we get to it. So, but the nice thing is that at this point, if you have a page fault, it does mean an invalid address. Now, it may be a bug in the kernel, or it may be that the user program has passed a bad address. It could be one of those two things, but otherwise you aren't going to see a fault at this point in Pintos. So anyway, getting back to the discussion, you have these three scenarios we have to think about. You have valid scenarios, invalid pointers passed to a system call, and kernel bugs. And you have to think about, how do I deal with these things? How do I identify which one of these things it is? Because it's just a fault. That's all you know, because the CPU calls your fault handler, and now you have to handle it somehow. So we're going to assume that there is a way to identify the valid scenarios. And I'll cut to the chase. I'll give you the secret. The OS kernel maintains information about what are valid address ranges for every process. So the OS kernel knows what addresses are valid and what addresses are not valid. We'll talk about all of that stuff in a couple of weeks, I think. There's this thing in Linux called a VM area struct, which it's a linked list that describes the address ranges that are valid in the process. Okay, So we have a way of doing that. And the question is, how do we identify the difference between an invalid pointer passed to a system call and a kernel bug? So I wanted to talk to you about this part because it's a very interesting mechanism. Linux has a pretty clever solution. And the solution that Linux has will inform how you should think about your system call implementation as well. Because the important question to ask is how much kernel code actually accesses user space. Most of the time, if you think about what you've done in the kernel so far, the kernel is accessing kernel data structures. The kernel is accessing stuff on the kernel stack, which, yes, the CPU put stuff on there from the user program, but it's now in kernel space. And it'll be accessing other kernel data structures, kernel code. And so if you think about the percentage of the code or the kinds of code that access user space directly, it's just the system call service routines. And it tends to be very small portions of the system call service routines. It's very limited, this interaction between user space from kernel mode. And so Linux actually has these macros, and they're really interesting. You don't have to know all the details of how this works, but the general approach is really cool. The Linux kernel implementation, the sources have these little macros that you can insert into your code to say, I'm going to start accessing user space. I'm going to end accessing user space. And during compilation, the compiler will build this thing called an exception table that keeps track of these address ranges of instructions that talk to user space. Then what happens is in the fault handler, the kernel goes through the exception table and it says, is the faulting address in any of these places that's talking to user space? If it is, it assumes that the address is bad. The user program passed a bad address. If it's not in any exception table, then the kernel assumes there's a kernel bug. Something crashed inside the kernel, or something did an invalid memory access inside the kernel. And if the kernel starts to go haywire, all bets are off. You can't trust reality anymore. And so what happens in the kernel is if one of these scenarios is ever detected, you get a fault, and it's not from accessing user space, but it's from some piece of code in the kernel that's not in a system call handler. This special thing happens called a kernel oops. And Linux will kill that kernel thread. By killing the kernel thread, it also kills the user process that's associated with that kernel thread. Oops, right? And ideally, this approach will allow the kernel to remain as stable as stable as possible. So this is one of those mechanisms that I think it's really clever. It's an interesting challenge to figure out how to solve these kinds of problems. And Linux has quite a clever solution. And so this is, if you've ever seen a kernel oops, this is a really old school kernel oops from Solaris, I think, because it's on this processor called a Spark. Your system made a Spark, and then you can see that it dumps out all of this information about the registers. This is a RISC processor, so it's got a bajillion registers. That tends to be typical for RISC processors. Okay, so hopefully that little bit of side information will also help you to think about how you are implementing your service routines and how to debug faults that you may encounter along the way, because it's almost inevitable that you will. The last thing to talk about today is Pintos, because I mentioned that Linux and Windows and Mac OS all interact with system call service routines. How shall I say this? The user mode program calls the system call by passing arguments in registers, and Pintos irritatingly chooses to pass arguments on the stack to system calls rather than in registers. I'm sorry, what can I do? I didn't design the assignment, but I have come to appreciate it over the years because it is great for getting students to think about how to talk to user space from the kernel. So system call arguments are on the user stack, not in registers. It does complicate the system call mechanism. But once you understand where all the information is that you need to access this stuff, you realize that it doesn't actually complicate it that much. So you have to understand your x86, let me be more specific, your IA32 interrupt dispatch mechanism and how that information is exposed into Pintos. So you can see here that you have the user process stack. I have current contents of the user process stack because it will be in some function invocation. At the very least, it'll be inside main. Remember, we always have to have a main, and main will do stuff, and main will call other functions, and that'll push stuff onto the stack, and functions will return, and that'll pop stuff off the stack. So the stack is going to have stuff in it. Well, at some point, the Pintos test program will invoke system calls, and the system call client code, or the stuff that lives in user mode, is going to push stuff onto the stack to invoke the system call. Then it's going to trap into the kernel. It's going to do int $0x30 because that's the Pintos interrupt service routine for traps, for system calls. And you're going to end up with a kernel thread stack that looks like this. Stack segment, stack pointer, pointing back to the user mode stack, the flags register, the instruction that was being executed when the trap occurred, error code and interrupt number. Error code will be a dummy value. I think it's 0 on Pintos. And then the register state of the interrupted program. Now you have a couple things in here. Stack segment, stack pointer. Hey, I can use the stack pointer to go access the user stack. And it really is no more difficult than that. Let me see what my next slide is. Yeah, I'm going to talk a little bit more about this picture because a picture is worth 1,000 words. When you push stuff on IA32, it's always 4 bytes. And so you can view this ESP thing as the start of an array of 4-byte values. Now you have to decide what type those values are, but you know they're always going to be 4 bytes. So you just index into that array and access the things that you need, pull them out, and you can use them in your service routines. The one wrinkle, of course, is that this is user space and the stack could be corrupt. So you have to make sure that you access user space carefully from the kernel. And the assignment write-up has plenty of information about how to do that. Interframe is the beast that exposes all of those values. I'm going to go back. You have all of this stuff that's on the stack. All of this stuff is exposed through interframe. Now, the way that C lays out data structures is important to understand as well. The first field in a struct gets the lowest address. The second field in the struct gets the next address. The addresses increase as you go down your struct definition. So the highest addresses are going to be these things at the bottom. Stack segment, stack pointer, flags, code segment, instruction pointer, error code, interrupt vector number, and so forth. So these guys are at the bottom of the struct, meaning they have the highest address. You go back to this slide and you see that's where this junk is. So it allows you to access the stack pointer. It allows you to access other stuff. You could do all kinds of stuff here, but we won't. In a few weeks or a few days, we're going to talk about how signal delivery works. I don't know how many of you are familiar with signal handling in C, but this stuff is used in some incredible ways, and I can't wait to tell you about how it works. But you see how you can access all of the machine context of the user program through the interrupt frame. Okay, so I talked about this. But yeah, so all you really need to do is access ESP, which is down here. As it says on the slide, access ESP, cast it to uint32t star, and treat it like an array. Index into it. Boom. You can just start accessing the stuff on the user stack. Now you need to be careful because you may fault, because this, if I remember correctly, I think there are Pintos tests that call system calls with an invalid stack. So, the Pintos tests are great. They really make you think about everything. So just a fantastic mechanism. Okay. The Pinto system call arguments are pushed onto the user process stack, and they follow the same cdecl calling convention that we already talked about. I shouldn't say they follow cdecl, they follow something akin to cdecl, so that the last argument is pushed first and therefore is at the highest address. The next to last argument is pushed second, so it's at the next highest address, all the way down to arg1, which is going to be at the lowest address. And then the system call number will be the very last thing pushed. So if you dereference ESP, you get that array pointer set up, and the first element, the 0th element in that array, is going to be the system call number, and you can dispatch on that. So easy peasy, right? Hopefully this should spell out how you can go about doing these things pretty easily. Okay, yeah, and also, like I say here, your implementation doesn't have to be as generalized as the way something like Linux works. So you can use the system call number to figure out how many arguments are required. A lot of students will have some code like in a switch block, or I would avoid a series of if statements because, well, I don't know, modern compilers can probably deal with that too, turn it into a nice efficient execution. But a switch block would be the best. And so you'll know for each system call number how many arguments it needs. And then you can pull the arguments into kernel mode and then pass them to the service routine, and you're done. Okay. Well, you got to write the service routines too, I guess. But anyway, it turns out to be a pretty straightforward mechanism to build, as long as you understand how the machine context and how all of this information is managed by the CPU, by the kernel, and how it's exposed inside of Pintos. Okay, is there anything else I want to say about this? I don't think there is. I think that's all that I needed to say for today. And that should give you plenty of orientation for the second Pintos project that you'll have to do. Okay, well, that's it for now. I'm going to go on to the next slide, which will give you the plan for the next few lectures. We're going to go through two topics that I think are very useful and interesting if you happen to love operating system implementation, but they aren't strictly required for any of the Pintos projects. So these are all enrichment lectures, if you will. We'll talk about signal handling, which is black magic, and it's the coolest kind of black magic. So we'll talk about how signal handling works. If you thought all this stuff with different stacks and machine contexts and all that kind of stuff was magical, wait till you see how signal handling works. And then kernel allocators will be the two lectures subsequent to that. If you think about it, modern kernels really need to manage memory, even though we have all kinds of clever things like intrusive linked lists, blah, blah, blah. So we'll go through the various historical approaches to kernel memory management and their strengths and weaknesses. And I think you'll have a really enjoyable time with that as well, particularly if you have a Mac, because Mac is built on top of Mach. And so it actually has the same programs that I talk about in the lectures from Mach and from BSD to ask the kernel allocator what's going on, and you can actually poke around a little bit and see what it's doing, and it's pretty neat stuff. So anyway, that's it for today. If you have any questions, I will hang out on the Zoom channel. Otherwise, I will see you on Wednesday.